Bismillahirrahmanirrahim. Just giving few seconds to Dr. Ali, and then we should start. And today I also intend to take a formative assessment, which will be just a 2-minute assessment. And don't worry about that, it'll be something very simple. So, we are studying group delay. In group delay, we discussed that from a system point of view, that every algorithm in signal processing is called a system. Any algorithm which you apply to a signal, to an image, to a video, to a signal coming from a sensor is a system. Okay, so in this course we are only restricting ourselves to learn about linear and time invariant operations that are linear and time invariant. We don't want to get into the complexities, at least in this course, on non-linear operations like taking log. There's a complete subject in signal processing which deals with non-linear type of operation like morphological signal processing, where you take minimum and maximum. Then there is another branch where you take logarithm of the signal, because if the noise is a multiplicative noise, then you, in order to separate it from the signal, you need to take a log, and then you do the signal processing. But our focus is only linear and time invariant operation. In this case, you have xn is your input, yn is your output, and a system can be characterized with an impulse response. And the relationship, only for an LTI system, relationship of input and an output is through convolution summation, which is a mathematical summation, and we have been writing it so many times in this course. H of k, x of n minus k by of n. Okay, and we know that for there are two types of system. One is finite impulse response system. The other one is infinite impulse response system. Okay, finite impulse response and infinite impulse response system. And finite impulse response system, this H is finite. H of n is finite. It only runs usually for a causal system from 0 to L minus 1. So this becomes a finite impulse response system. An infinite impulse response system, we don't use convolution, rather we use a difference equation. And difference equation is y of n plus a1y of n minus 1 plus a n y of n minus n. So this is an nth order difference equation is equal to b naught x of n plus b1 x of n minus 1 b m x of n minus m. So this is how we implement an IIR system, which is an infinite impulse response system, and its h of z transfer function is written as b naught plus b1 z inverse plus bm z minus m divided by 1 plus a1 z inverse a n z minus m. Okay, that's how you write the difference equation. And then another important aspect of this is studying this in frequency domain, because we want to study this in frequency domain. The same convolution summation will change into multiplication. So summation changes into multiplication. So you write it like this: y exponential j omega is equal to h exponential j omega into x exponential j omega. So this is important, because once we are implementing, we implement a difference equation. So this chapter only focuses, the first part of the chapter only focuses on IIR systems. In IIR systems, once you take Fourier transform, usually h is complex and x is complex, because once you are multiplying two complex numbers together, you need to study that how their magnitude behaves, and then you also need to study how their phase behaves. So we know if you are multiplying two complex numbers together, okay, and preferably you write them in polar form, and polar form is r1 exponential j theta 1, we know that, r2 exponential j theta 2. So magnitudes, they multiply once you are multiplying to complex number, and phases they add. So this we already know. So on similar basis, once you are multiplying the Fourier transform of h with Fourier transform of x, their magnitudes will multiply and their phases you add. So you can write it like this: y exponential j omega magnitude is equal to h exponential j omega magnitude x exponential j omega magnitude. Okay, magnitude they multiply, and we have seen, and I've been telling you this, that h is like a Caesar, that you basically tailored the frequency response of x according to h. So whatever you want that should remain in the signal, you make h equals to 1, and whatever you want to remove, you make the h equals to 0. So once you draw h, usually you draw it like this, ideal response. So whatever you want to let pass, magnitude is 1. Whatever you want to stop, magnitude is 0, because of h multiplying with x. So it'll eat up all the frequency contents. So this is omega. This is an ideal filter. This is an ideal h exponential j omega. But in this section, or even in this chapter, we are more focused towards the phase, that what role phase of this h plays in corrupting the phase of x. Because as this relationship is telling us that at every frequency you are passing through the system, the phase of h will be added in the signal. Okay, so this is also called phase distortion, that I don't want to change the phase of the different frequencies in my signal. I hate that it should change the phase of different frequencies in my signal. But for getting the benefit of an IAR system, which is in terms of less amount of computation, I got to live with this, that phase is going to change, the phase of x will change, and the only way we can make this corruption to be zero, this corruption of phase to be zero, to not affect, is to make it equal to 0. So the first attempt, obviously everybody would try to do, is that it'll make phase of h exponential j omega 0 for all frequencies omega. Ideal. Because something is adding into the phases, so make it equal to 0. What is the big deal? But in order to make the phase equal to 0, your only way is that your h should all real. H should be all real. The frequency response should be all real. What is the practical application of phase of a signal? It is not practical application. Phase of a signal is usually, a signal is nothing but sinusoids. So phase is like if you have a sinusoid, for example, this is a sinusoid, okay, and you pass it through an LTI system. So LTI system will change its phase. Now it may start from here, okay, it may start from here. And if you have different frequencies in the signal, okay, you have, because the signal is nothing but combination of different sinusoids. So if a sinusoid, all the different sinusoids will delay by different amount, so it will distort the shape of the signal, okay. It will not change the frequency, it will distort the phase, the shape of the signal, which we don't like in many applications. In many applications like ECG, I don't want my ECG, which is something like this, to appear. This gets delayed and this goes here, and if you go to a doctor and he will think that you have a heart attack because your ECG, the different frequencies in the ECG signal has changed their relative positions with respect to each other. So phase is nothing but it is where the sinusoid starts. So that's why phase is an important aspect of a signal, because every signal is nothing but bunch of frequencies. So that's why phase is important. I don't want the different frequencies to be delayed differently, and that's why instead of looking at phase, we look at negative derivative of the phase. So this is what the group delay is, minus d over d omega of the phase response is called tau omega. This is called, and its units are number of samples. Means how many samples every frequency will be delayed. It's a function of omega. That is a dangerous thing, because different frequencies can be delayed by different number of samples, which I don't want. I want like a linear, that every frequency to be delayed by the same number of samples, so that shape is preserved. Okay, so we studied that the phase distortion is to either be 0 or the group delay should be such that it is a constant, that for every frequency group delay ideal is that it should be a constant. Okay, so that my shape should not, I don't mind a digital signal to be delayed a little, but I want that to remain as it is. If the question is, sir, is it not the orientation of the frequency content to each other independent of phase? No, that is what is a phase is. You know what is phase? Phase is cosine of 2 pi f naught t plus phi. This is called the phase. Phase is this, okay? Cosine of 2 pi f naught t plus phase. If phase is not there, then it is simply a cosine, which will start from 1 and it'll go with like this. But if phase has 30 degrees value, the cosine will start from here, okay, like this. So it will be 30 degree, cosine of 30, it will start from cosine of 30 degrees. This is called the phase. So phase is this. IR system group delay distorts the signal. Where can we use IR? No, we can use IIR system where, number one, if phase is not important for you, in many applications you are only worrying about the frequency contents in a signal, or you try to make sure that you basically whatever distortion IIR system has caused to your phase, you correct those distortion. So you put another system which does not change your frequencies and will study this and will only fix the phases. It'll say, oh, go back, and it'll make the signal as if, or you design an IIR system where at least the frequencies which are passing through the system, you try making the phase constant. Okay, so phase is an important aspect and we use IIR system because of these reasons. So phase, understanding phase, I hope you understand. Phase is nothing but in a cosine, once you have a simple cosine, there is a phase in it. This is the phase. Okay, a signal is nothing but many frequencies and every frequency has a different phase in the signal, and you pass it through a filter and this phase changes for every frequency which you don't like. Okay, you don't like this phase, any change in this phase, because it will distort the shape of the signal. You must have done a lab also in order to just figure out this. Okay, could please repeat why we cannot set phase? Yeah, that's a good question. Why cannot we put the phase of H equal to 0? This is a good question. Remember that we have studied in chapter 2 where we were studying discrete time Fourier transform properties. And we studied that if your signal x of n is real and even, only then your Fourier transform will be real and even. Okay, so this is what we have already studied. If your x of n is real and even, only then your x, or if we instead of x write h to be more, because we are concerned about h. So x of n is real and even, then h exponential j omega will be real and even. Means real and even means if you have a sample here, a sample here, a sample here in your impulse response. Okay, this is 1, this is 2, this is 1. This is the only way that you make phase of h goes to 0, because as you can write, its Fourier transform, it is exponential j omega plus 2 plus exponential minus j omega. And you combine these two, this will be 2 cosine of omega. Now you don't see any j in it. Okay, so it has only magnitude. So this is an h where the phase of h is 0 because it has only real part. Any complex number which has only real part in it, it does not have any phase in it. Okay, so phase can only be 0 if you have a symmetrical impulse response. And this, there is a problem with this. The problem is it is non-causal because it starts from -1. Number 1 is non-causal, and number 2 is it is not an IIR system. It is an FIR system. The simplest IIR system, the simplest of all IIR system is y of n is equal to ay of n minus 1 plus So this IIR system cannot go simpler than this. This is a first order IIR system, and we have done this many times, if you find its h exponential j omega, it is 1 over 1 minus a exponential minus j omega. Okay, and its h of n is a of n u of n, the simplest of the IIR filter. And if you plot this, it is like this. No matter what you do to h of n, you cannot make it a symmetrical signal, which is on both sides looks alike. It cannot. So means IIR system cannot be zero phase. Okay, IIR cannot be zero phase because they are decaying exponentials. They start and they keep going down, 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 down. No matter where you shift them, okay, you cannot make them zero phase. FIR, yes, you shift them, you can make them zero phase because they are sync. The FIR, on the other hand, are not A and U of n. They are a truncated sync, and we know that. You take this, you take its inverse Fourier transform, and you get sine omega Cn over pi n. This is how an FIR filter is made. And if you plot this, it is a sync which is symmetric. And you truncate it to make it an FIR system. Okay? So, by construction, FIR is a symmetrical filter or impulse response, so you take it and then you shift it. So it is first zero phase, and then once you move it, it becomes a linear phase. There is a linear, and we have done this in last class as well, that if you have, for example, this, and it is 2 plus 2 cosine of omega, so you can make it causal by shifting it to 0. A shift in time is multiplication by an exponential minus j omega. Okay, so the phase becomes r exponential j theta, so phase becomes minus omega. Minus omega is a linear phase. Okay, so phase becomes linear if you have an FIR filter and then you shift it. So FIR filters, this has h exponential j omega. This h exponential j omega has a phase, has no phase in it. Okay, if you take its magnitude, this one, it is magnitude is 1 and 0. Till cutoff frequency, magnitude is 1 and otherwise it is 0. So there is no j in it, as you can see here. So this is the impulse response, and then you shift it, and then you shift it by alpha. So n, this expression becomes sine omega c n minus alpha pi n minus alpha. So this is how you make an FIR, and then you truncate it. You shift it and truncate it, and you got there. So shift, what the shift will do is, it will bring an exponential minus j omega. This one will be multiplied by exponential minus j omega alpha. So this brings a phase in it, but it's a linear phase. So its phase is complex. We will shortly see what is the phase of this. Okay, it is going to be a non-linear function of omega, and this h even has zero phase, but once you shift it, it has a linear phase, which, and group delay is minus, so it is group delay tau of omega is equal to minus d over d omega of minus alpha. So it becomes alpha omega. So this is the phase. So minus minus cancels out, it is alpha, which is the amount of delay you inserted in the filter. So this is the group delay. So once you are designing, and I hope that you have done these labs, Uh, so I have, like, again, you cannot set the phase to 0 because it will make the system non-causal, and we don't want non-causal system, because for a phase to be 0 it has to be evenly symmetric. A sample here will have a sample here, so you cannot have a 0 phase system. In image processing, yes, you don't care, you can have a 0 phase because you have all the future samples. Yes, shifting by alpha brings a linear phase into your signal. Shifting the whole sync by alpha brings a linear phase in the frequency response, which is okay because it's just delaying the whole thing, and you are not distorting the shape of the signal. So this must be, remember that this thing, because you will be using even in your IoTs and whenever you are processing your signal, a temptation is just use a simple IIR, because with very less computation you can filter out the noise and stuff which you don't like. But please go back and look at the group delay response, that is it going to distort the shape of my signal? Is shape important for me? Is shape not important for me? And in many applications you may think that perhaps shape is not important, so you don't care about that. And in some, the phase, for example, in digital communication, in phase modulation, the entire information is in phase of the signal, because if it is 0, you have 0 phase, and you must have studied digital communication. If you are sending 0001 1011, so the entire information 0001 1011 is hidden, or is basically coded in the phase of the sinusoid which you send for some time. For example, for 00 you send a cosine, for 01 you delayed by 90 degrees, okay, so it goes like this. For this you delayed by 270 degree, 180 degrees, then 270 degrees, so 90, 90, 90. So 0, 90 degrees, 180 degrees, 270 degrees. So you are just having different types of cosines being sent for the different encoding, the different bits. So information is in the phase, and you say, oh, I don't want my phase to be distorted. So the phase is important, and the amount of phase distortion is measured in terms of group delay. That also you need to remember, that amount of phase distortion is the deviation of your group delay from a constant value. So amount of phase distortion is measured deviation group delay from a constant value. Okay, so I don't mind if a group delay is constant, because I know a constant group delay means only signal will be delayed by these number of samples, which is inherent in any FIR system. It will just show you constant, that once you input a signal, let's say this is your signal, so this signal has a high frequency noise, and you want to basically remove this noise. So you want to filter out this noise, which perhaps is caused by heating up of your electronics, or this noise is coming from your electronics, and you acquire the signal and you say, oh, this there is a high frequency noise, let me filter this out. So you pass it through an FIR filter, and once you pass it through an FIR filter, what the filter will do, that it will first remove all the noise from the signal, and then it'll make it delay by certain. So if it's starting from 0 and you have like 25 group delay, so it will start from 25, and this will be nice filtered signal without any noise in it. Okay, and you say, I am okay, I don't care, because if I'm going to play, I know that there will be few millisecond delay in the signal. Like I'm talking on Facebook, and there's a little delay that because the signal is being processed in a way that it is processed through all linear time invariant systems, so that you only see a delay but no distortion. So delay is acceptable in most of the applications. We know that every signal processing system has some inherent delay because the signal has to be stored. It has to be passed through an LTI systems. Every LTI system will cause some delay. So I say I don't care about a delay, but I would care a lot if it would distort the shape of my signal. I'll be very annoyed if this happens. So amount of distortion is measured, the deviation of the group delay from a constant value. Ideal is a constant value. It cannot be zero. Zero means it's an anti-causal system, okay? So you say non-causal system. So you say, I know that zero is not possible, but okay, I don't mind if it is a constant value, because constant value is telling me my signal will be delayed by these many number of samples. So I don't care if signal is delayed by these many samples, as long as it is keeping the shape and removing the unwanted components from my signal. So I am happy here, okay? So now we know that group delay is important, and you have no control over the group delay of an IIR system. You have control over group delay of an FIR system, because there you can always make it look symmetrical and then shift it by an amount alpha. So we studied this, and then I showed you different examples where we plotted group delay of IER and FIR filter, and I hope in the lab you also did this exercise to understand more about the group delay. And now we need to understand what the location of zeros and pole does to the frequency response and phase of your system. So because so this is location of poles and zeros. Though we have learned that how to plot the poles and zeros of a system, because the transfer function would look like this: B0 plus B1 Z inverse goes like this, BMZ minus M, 1 plus A1 Z inverse plus A2Z minus 2. So this is my transfer function, okay? And change Z to exponential minus j omega, it becomes my frequency response. You must have noticed that throughout this course, we're just dealing with an LTI system. If it is an FIR or IER, so it has a transfer function and a frequency response and an impulse response and a difference equation. So we just keep dealing with these few things even once we study implementation, and so many things that we are not going to go away from this. So you must just remember this by heart, that this is what system in signal processing is, that you are just dealing with this expression or this. So you are dealing with coefficients B's and coefficients A's. So in all your DSP life, you are just dealing with coefficients in the numerator, coefficient in the denominator. Coefficient in the numerator are the coefficients of X. Coefficient in the denominator are coefficients of Y, or this is the frequency response, okay? So in mth, or this is n. So m means there are m zeros and n means there are n poles, okay? You factorize this, and you can always find the location of poles and zeros, okay? A good signal processing engineer could look into the poles and zeros and can roughly plot the frequency and phase response, okay? Because your life is all around these poles and zeros. So you want to really learn that, oh, this pole here, what does it mean if it is here? Okay, once you plot, so you will see always there will be a circle. So all tools will draw a unit circle. This is an important, and you know why. All tool will draw a circle, like MATLAB also. Once you do pole zero plot, it will always draw the circle to show you that the circle is your lifeline. If you go out of it, you are no more. Okay, so the circle is where you are stable. You poles in the circle, you are stable and causal, and you are on the circle, or you go out of circle, you are gone. So the life of a pole must exist only inside the circle. Zeros no matter. ठीक है, जो zeros हैं वो कहीं भी जाएं हमारी बला से. So you are not worried about the zeros, but you are worried about the poles, because poles are the feedback element. These are where your coefficients which multiplied with your output y of n minus 1, and they are going to come back into your signal, come back into your input, adding into your input, and you want to deal with poles very carefully. The poles are basically the determining factor as far as the stability is concerned. And so a shape like this is telling you something, okay? And you need to know, because you are a signal processing engineer, you need to know what is it telling me, what a location of a pole tells me, location of zero tells me what, okay? Because just looking at it, you should say, oh, this is this. And so location of poles and zeros, the only thing at this point you can tell is whether it is stable or not, stable and causal or not, because you know the region of convergence is outside the outermost pole, and you can very conveniently say, oh, this is the outermost pole and the region of convergence contains unit circle, so it is a stable system. And we know the stable systems are where all the poles are inside the unit circle, or causal stable system. But now I want you to consider a simplest system which has only one zero in it. H of z is 1 minus r exponential j theta z inverse. A signal processing system cannot go simpler than this. This is an FIR system with only two coefficients. One is 1. So this, if I plot h of n, so h of n is delta of n. This is a constant thingy, delta of n minus 1. So this is the simplest FIR filter with two coefficients. And intentionally I have made one complex so that you understand dealing with the complex numbers, okay, intentionally. But usually you can say, let's example is this. This is a simplest FIR filter with two coefficients. You take the current sample and you subtract the previous input sample, x of n minus x of n minus 1. So this is a system which can be written as this, x of n minus x of n minus 1. So simplest system that you're just a difference. This is called a difference. That you're taking the difference of current sample from the previous to make a current output. So you have the previous, so you just keep doing this, subtract from the previous, subtract from the previous. So this is the simplest. And we just made it a little interesting by multiplying this with r exponential j theta. Why on this earth would you ever do this? And we will shortly find out. Why would you ever multiply? Why would you ever have a coefficient which is complex? Usually you don't like a coefficient to be complex for sure, because this then brings in your time domain brings complex numbers in your time domain output, which you don't like. You hate to have outputs which are complex in numbers. So the simplest of this h of z, 1 minus r exponential j theta z inverse. So this, if I ask you to plot poles and zeros of this, so you will say z minus r exponential j theta over z. Okay, so you take this z inverse goes down, so you can write this is the simplest of FIR filter having only two coefficients in it, and its z transform has 1 0 and 1 pole. How do you compute the roots? By putting this equal to 0, by putting this equal to 0. So if you plot this, okay, so your 0 is, you put this is equal to 0, so z is r exponential j theta. This is your 0 of the system, and z is equal to 0, your pole. So this is your pole, this is your 0. And now you need to remember how to plot r exponential j theta. So you have been doing this in your mathematics courses from your high school maths, that it is just a polar form of a complex number, which is only telling you that this point is r in magnitude and theta is in angle. So this is r exponential j theta, and z is equal to 0 is a cross. Okay, so you plot the pole with a cross and you plot a 0 with a 0. This is how you plot. And obviously it's important that you plot the unit circle like this. So it's important that you plot the unit circle. Okay, so this is a circle with radius 1. So this is, and now what I want to study is, what is the significance of this 0? What if I move it here on the real axis? So can I move, like what happens once I start moving this 0, okay, in the complex plane? First I can move it without changing the radius, or I can place it here, place it here, place it here. So there is a tool in MATLAB where you can design a system by yourself placing poles and zeros in the complex plane and then seeing that how the impulse response is changing. But my interest is how the frequency response changes as well. So by changing the location of the 0, what is the change in the frequency response of the system? Because I am really concerned about a frequency response where I want some frequencies to go past and rest of the frequencies to be stopped. So this is the whole purpose of a system, a linear system in signal processing. What you are studying in this course, the whole purpose is to let some of the frequencies go unaltered, undamaged, and rest you want to kill them all. You want to kill the rest of the frequencies. So what is the role of a 0 in this? A 0 in this place, does it has anything to do with where I want my frequencies to be 0? Has the location of the 0, especially this angle, has it any role? Because I know my digital frequencies goes from -pi to pi, and so is this circle goes from 0 to pi on this side, 0 to -pi on this side. Has this location any role in shaping the frequency response of my system? And location of this pole has anything to do with my frequency response? Obviously it has everything to do with the way your frequency response is shaped. So by looking at this, I can say something about that how the frequency response is going to look like. If I move this, so I now want a way of moving this 0 here and moving it left and right. So interestingly, in MATLAB you can actually do this physically as well, and maybe Dr. Ali will prepare a lab where you place a 0, look at its frequency response, and then play with this. Bring it here, go take it away, and move it somewhere, move it somewhere, move it somewhere, move it somewhere, and keep seeing that how just the simplest system with 1 0 changes the frequency response if you move it around. So but let's try to make a mathematical rationale of this, that mathematically can we actually prove that it has some significance on the shape of the signal. So to do the math, I need to take its consider the frequency response, because I want to see how the location of a pole or a zero changes the frequency response of a system. So this becomes exponential, or I can say 1 minus r exponential j theta exponential minus j omega. So this is how I started. So we know that if you replace z by exponential j omega, it becomes the frequency response. So this is the frequency response. And I want to have the magnitude of the frequency response, expression for the magnitude, and I want an expression for the phase of the frequency response, because I want to study both, that how the phase of this changes and how the magnitude changes. And you know how to calculate the magnitude. You compute the magnitude by multiplying it with its conjugate, and that gives you the square of the magnitude. So multiply this with its conjugate. So you can do the maths by yourself, and we have done it actually last time as well. Exponential j theta exponential minus j omega, multiply it with its conjugate. Its conjugate is 1 minus r exponential minus j theta exponential j omega. If you do this multiplication, okay, multiplying a complex number with its conjugate, you will find out that you get this expression: 1 plus r square minus 2r cosine of omega minus theta. Okay, this is, and the square root, the square of this magnitude is this. This is the expression. Okay, and then phase is also, let's not at this point worry about the phase. Let's just focus on the magnitude, and we'll come back and worry about the phase as well. So let's not do that. This is, the expression. And if I ask you a very simple question, that there is this theta. Okay, what is omega? Omega is frequency which goes from 0 say 2 pi. This is what you are plotting. You are plotting changing omega value, and you are plotting the frequency response going from 0 to pi, or from minus pi to pi. This is omega. Omega is the frequency. Once you are plotting, you put a value. For example, if you put 0, you will get the response at 0. So you keep changing omega. Theta is fixed. Theta is the location of the 0. So theta, location of the 0. And so now what you want to study? What if I change my theta? Okay, theta angle, if I change, move it down, move it up, or I change its location on the same line, how is going to change my 1 plus r square minus 2r cosine of omega minus? It's very trivial here. For example, when do you get its maximum value? Because you are subtracting something. Okay, so you will get a minimum value. A minimum value will come once cosine is 1. Once cosine of omega minus theta is 1, then your value will be 1 plus r square minus 2r. Obviously, this value also depends upon r. Okay, value depends upon r as well. Okay, where the 0 is. For example, if the 0 is at 1, right on the unit circle, r is 1, so you get 1 plus 1 minus 2, 0. So you get value 0. So this expression is important. So let's now try to dissect, and let me just so this is the expression, and this expression is for frequency response of a system with a 0 at r exponential j theta. Okay, it is what it is telling me is that once this value is 1, and when this value will be 1, once cosine of 0 is 1, cosine of 0 means that omega minus theta is equal to 1, means omega is equal to theta. Once omega is equal to theta, then this expression will have a minimum value. So if you are plotting, let's say theta is 30 degrees, this is 30 degrees, or pi by 6. Pi by 6 is 30 degrees. So if you are plotting exactly at pi by 6, the frequency response will dip, okay, and then will go up. And when will it have a maximum value? You know, a cosine has, once it is equal to -1, okay, because if it is -1, then minus minus plus. So this value is 1 plus r square minus 2r, and you can also write this as 1 minus r square. This value is 1 minus r square at theta. So your frequency response is going to dip and is going to be maximum after 180 degrees, after pi. Because once omega minus theta is pi, okay, or omega is equal to theta plus 180 degrees, then it goes to maximum value. So now I know that wherever I place a 0, I see a dip in the frequency response. So this answers my questions that what the omega c, which is the dip, has to do with the location of a 0. Because where there is a 0, okay, the frequency response will come and dip here, okay, will dip here and then it will go up. So a dip is at theta. And how much is the amount of dip? It depends the location, because this value is 1 minus r square. Okay, the amount of dip will be controlled by the location of a 0. So 1 minus r square, if r is equal to 1, the dip will touch the 0. It will just kill that frequency. So it will come down to 0. In which case, once you have placed your 0 exactly on the unit circle, any frequency you want to kill from the incoming signal, you make sure that there is a 0 placed on the unit circle at that frequency, because we know wherever there is a 0, the frequency response will come touch base and will go up. A touch base here. Okay, it'll touch down. It'll touch down, tick, and then it'll go up. Okay, this is the 0. If you are placing it right on the unit circle, it will do this. If you move it away, okay, and then it will not touch, it will come very close and then it will go away. Okay. So this is what the location. And if you change this theta, then the location of dip will change. I'll say now I'm dipping here. If you bring it here. If you bring a 0 here, it will dip at 90 degrees. If you bring a 0 here, it will dip at this. And if you put many zeros right on the unit circle, so what it is going to do, so you say, wow, why should not I have, this is my unit circle. I have a 0 here, 0 here, 0 here, 0 here. So what all these zeros are going to do to your signal? So it said dip, it will try to go up, then again dip, it will try to go up, then again dip, it will try to go up, and again dip, it will try to go up. Because wherever you are placing 0, and then it will go up. Okay? So wherever you are placing zeros, it will bring the response back to 0. It will bring it back to 0, bring it back to 0. So this is the effect of placing multiple zeros, that it will not let your signal go up, and means that all these contents will be filtered out. So wherever you see a large concentration of zeros in your frequency response closer to the unit circle, it means that that frequency response is going to kill all those frequencies which are, and remember in FIR you don't have poles, you only have zeros. So zeros will be placed to the frequencies which you want to kill, okay, in that part of the circle, the frequencies which you want to. If there is only one frequency you want to kill, you just place a 0 on the unit circle, and it'll make sure that frequency will never get out of the system, because a 0 at a particular frequency means you're going to kill that frequency. Okay, So this is how the location of 0 plays an important role in shaping the frequency response of a system, as is very obvious from this, which is the magnitude square. The magnitude square response, this where R, we understand the significance of R, and we understand the location theta. R means that how close you are from the unit circle, and it'll tell you the amount of dip you are going to have at this angle, and this theta is going to tell you that where it is going to get into a dip and go up, dip and go up. So this is, if you have a, this is interesting, this is a FIR filter with only 2 coefficients in it, first order, you can call it first order. What if you have a pole, means you have only a pole in this? So what will happen? So a pole is, so you are changing the h of z to be 1 over 1 minus r exponential j theta z inverse. So your transfer function is z divided by z minus r exponential j theta. So you are changing the location of poles and zeros. Okay, no problem. The importance of unit circle is. Now what happened is the same expression now is appearing in the denominator. Exponential j omega 1 over 1 minus r exponential j theta exponential minus j omega, and the magnitude square is going to be the same expression, 1 plus r square minus 2r cosine of omega. Nothing changes, only now it is in the denominator. Means this distance which we just discussed is 1 over, first it was like how far you are, because it comes out to be, if omega is equal to theta, this expression comes out to be 1 minus r square. Now it is 1 over 1 minus r square once omega is equal to theta, and I want to see the dip phenomena, so where it is going to dip. A 0 going to dip at an angle theta, but 1 over this means a pole is going to go up, the frequency response will go up. Okay, how much amount? It depends upon where you are placing your pole. What if you place your pole right on the unit circle? So you get a 0 in the denominator, 1 over 1 minus 1 over 0, and 1 over 0 is infinity. So if you place, and this is where it makes a pole, it goes to infinity. As your r, you're changing r, and r means that wherever you are placing this pole, your frequency response is going up on that frequency. If it is a 0, it is giving a dip, but 1 over dip is going to go up. And if it is right on the unit circle, if it is a 0, your frequency response will dip and touch 0, but if it is a pole, your frequency response will go to infinity. Okay, so converse is, wherever you are placing a theta, the frequency response will go up. Okay, it will go up at that. This is the frequency it will pass. So location of pole in the frequency response will tell you what frequencies are going to be passed from the system. So wherever you place a pole, it means you want to bring your frequency response up. Okay, because how much up depend upon this distance, that how small is this distance. If you have 0 distance, it is going to infinity. So by changing the location of the pole on this line, you are changing the height of your frequency responses. So it is this or this or this or this or this, okay, depending upon r, value of r. And this is where your theta is. And if you, so whatever frequencies you intend to pass, you place poles there, and whatever frequencies you want to stop, you place zeros there. So you will see the location of poles and zeros are very meaningful in a frequency response. That the frequency, if it's a low pass filter, you find all the poles here in the low pass region. If it is a high pass filter, you will find poles placed here. If it is a band pass filter, you will find poles placed here. So locations of poles and zeros will determine the shape of the frequency response because of the simple relationship that we have studied, that it is 1 over 1 minus r square. There is yet another representation that will give you even more mathematical rationale of placing poles and zeros. And as I mentioned earlier, perhaps in your next lab, I would love you to play with by yourself placing a pole and a zero in complex plane and see that how the shape of your frequency response changes. That will give you a lot of understanding and comprehension that how the locations. But once you are designing, you are not designing by placing poles and zero. You want a magical way of designing a low pass filters which should do what you want to do. And then you go back and see their location. You say, wow, these, I know that. Cannot I just go and place these poles and zeros myself and get an H of C? Yes, but through lot of trial and errors, and you just keep moving them to bring the shape of your frequency response into that category. So I think this is where I want to take a 2 minutes. It's not a quiz, but it is a formative assessment. Let me give you some time to prepare. So how I want you to do this is that I'll write a question and you send this, preferably an email to Dr. Ali, the answer, and you will have only 2 minutes. So those who would send it within 2 minutes, we will count the answers and we'll grade them. And if you take more than 2 minutes, then your answer will not be considered. So 2 minutes and ready, set, go. So paragraph, why do you want group delay to be a constant? How you achieve it? Or you can inbox me as well. Right in the Facebook, just write like few lines, 2 minutes, and inbox. Why do you want group delay to be a constant, and how you achieve it? How you achieve a constant group delay? Dr. Ali has also sent his email address. So your 2 minutes start now. Okay, so this is so time is over. Uh, so we will only consider answers till now. If you have already sent me, okay. Otherwise, so let's. So there will be another summative assessment in a while. Okay. Good. I hope that most of you have actually done this. So now let me go back and look at this system which has only one zero in it. It has taken the shape of a heart. I'm sorry, I do not intend to make a heart, I intend to make a circle. Okay, so this is a system with h of z is 1 minus r exponential j theta z inverse. This is theta, this is r. Okay. So this is our 1 minus r exponential j theta z inverse. So I'll be taking another 2 minutes assessment at the end of this session. So just make sure that you pay attention to this part, okay? 1 minus r exponential j theta z inverse. And in terms of, so this is z minus r exponential j theta over z. And in terms of h exponential j omega, it is exponential j omega. Z is written as exponential j omega if you're taking the frequency response, we know that. R exponential j theta over 1 exponential j omega. This is very interesting. This one, now look at this. I'll make it a little bigger here. And this is my 0, this is theta, this is 1. So this vector, if I think this in terms of a vector, is r exponential j theta. Let me, and there is unit circle, which is, this is the unit circle, okay? This is the unit circle, and once this omega, remember, you are just moving on the unit circle. At what value? And Fourier transform is Z transform on the unit circle. So if I want to calculate my Fourier transform of this frequency, then this is my omega, this is 1, and this become 1 exponential j omega. So these are the two vectors I am dealing with. This vector represent 1 exponential j omega. Let me call this vector v1. This vector let me call v2. And then there is a third vector, which is this vector. Let me call this v3. So now I have three vectors. One is v1. And we know head and tail rule. Head and tail rule says v2 plus v3 is v1. So v1 is equal to v2 plus v3. Then v3 is going to be equal to v1 minus v2. What is v1? v1 is 1 exponential j omega. What is V2? V2 is equal to R exponential j theta. So if you look here in vector form, this is vector V3 in the numerator, and 1 exponential j omega is a vector V1 in the denominator. So this is an interesting interpretation of the frequency response, that it is actually vector V3 divided by vector V1. This vector divided by this vector. So we know that in vectors, you have studied this in mathematics, and this will also give you a reason why you study mathematics. Usually people ask. So you have studied vector algebra, so linear algebra. So vectors, once you are dividing two vectors, so the magnitude of this will be the magnitude of V3 divided by magnitude of V1. What is magnitude of V1? It is unit, the 1, so you have only magnitude of V3. It's a very interesting expression, that the magnitude of exponential j omega 3 at different values of omega is just length of this vector. Whatever is the length, so is the magnitude of the frequency response, length of this vector. And phase, you also know from your algebra, that is, it is the angle of V3 minus the phase of V1 using the vector algebra. This is how they are related to. So, sorry. So it is this angle, this is angle of V3, and minus V1, angle V1 is this omega. So this is how you basically calculate the phase. Now, if I want you to plot the magnitude response of a system with 1, 0, this tells me just find out the length of the vector from the unit circle at that angle. Means that at this frequency, my magnitude will be this much. And as I am moving, my magnitude of V3 is changing. I have a minimum value of the magnitude once my omega is right and on theta, so it's going to dip here because of this reason, because length is the magnitude. Length of the vector, this is called a zero vector. Length of zero vector is the magnitude of the frequency response. Where is this length changing to minimum? Once you are right here, and then you are moving, the length is increasing, where you have maximum length here. Once you are 180 degrees away from the zero. And how much is the length? It is, this length is 1 plus r. How much is the length here? It is 1 minus r. So now we understand why the frequency response takes a dip at location 0, and the amount of dip is equal to 1 minus r. So once you are going to plot, let's say theta is 30 degrees, so your frequency response, let's say r is 0.8. So the frequency response will come down to 0.2, magnitude of the frequency response. So 0.2, 1 minus r. And then it's going to go up, and it'll take the maximum height of 1.8, where 30 plus 180 degrees, 180 degrees pi. So the length of the zero vector divided by length of the pole vector, and similarly is the angle. So once you are here, so your both angles are 0. Angle of this, basically both are going to be 0. So phase will be 0 at this location. The phase is also you can plot, but magnitude is interesting. So now I can say that just remember, wherever you plot a pole, a 0, let's say a 0 is here at 0.8, and this is your unit circle. Frequency response is length of this vector. length of this at different frequencies, length of this vector, length of this vector, length of this vector, divided length, because 0 pole is here, so its length is going to be sorry, it's not, so length of this vector, length of this vector, length of this vector, length of this vector. So this is what 0 is going to do to you. And if it is 0.8, so I can actually roughly calculate, the magnitude, but I know at 0 angle, this is 0 degrees, I am going to have this length equal to 0.2, so it will be 0.2 here, okay, and then it is going to go up, and exactly here 180 degrees. If the frequency response is at center of the circle, so we will get no dip no matter the angle. Not really. If it is, you means this, the 0 is in the center of a circle. Let me do that also. Okay. So this is going to be 1.8. Now what you do is change from 0.8 to make it equal to 0.9. Change the location of the 0. Now here the length will be 0.1. So here the dip will be more. It will come down to 0.1. And then it'll go up a little more, and here it will be 1.9, right? So now change it in the middle of the circle here, perhaps, if this is your question, middle of a circle, okay? So at 0.5, middle is 0.5. So it's still going to get a dip, but the dip will be, because length here will be 0.5, so it'll come down to 0.5, and it'll go up to 1.5 like this. So 0.5 to 1.5. So this is what is going. What if it is here at 0? So length is 0. Okay, so length will be 1. If you place a 0 here, the length will be 1. So if length is 1, then you have actually you don't care about that. Then that is the only case the length is going to remain 1 no matter at what frequency you are. So placing a 0 here, okay, and when do you place a 0 at 0? This is a 0. 0 is if you have an h of z which is equal to 1. H of n is delta of n. It has just a 0 at 0. So it means it is not going to change anything. So placing a 0, you can move it along this line. So dip will be at angle 0 degree and it'll go up at 180 degrees. What if you put a 0 here? Okay, at 0.6 but at 90 degrees. What will happen? Okay. So what will happen now, that your dip will be 90 degrees. So your frequency response will dip at 90 degrees. How much it will dip? 0.4. 0.4. And then it'll go up. So if this is 90 degrees, it will go up 90 plus 270 degrees. And 270 degrees, it will be 1.6. Okay. So the location of 0 is going to shape the frequency response of your signal, because the frequency response is nothing but it is the magnitude of the 0 vector divided by magnitude of the pole vector, because pole is placed here, so magnitude of pole vector is always 1. So that's why we are not really worried about that. And in the inverse case where you have a pole here, so remember h exponential j omega magnitude is length of 0 vector divided by length of pole vector. Remember this, I am going to give you a formative assessment based on this, okay? Just remember this, length of the zero vector divided by length of the pole vector. Okay, so should I or should I not? We are just setting the end of the class. Let me not, and in next class I'll ask you about this. So if you have a, so this is, I will ask you a question like this. Okay, there is a pole at 60 degrees, length is 0.6, and a 0 at 0, length is 0.8. Okay, so for example, and then we want to plot the frequency response. So you have to, at, let's say at this frequency or this frequency, so you have to draw a zero vector and you need to draw a pole vector and roughly measure length of this and divide it with length of this, and that's it. Length of this and length of this. Once you do that, you will know the free. So everywhere, wherever you want to find out, you do this. And we know wherever there is a zero, the frequency response will come down, take a dip, try to take a dip. And wherever you have a pole, it'll go up. Okay, because 1 over, so if instead of a pole there is a 0, so 1 over 0.2. 1 over 0.2 is 10 over 2 is equal to 5. So if you have a pole, the pole will take the response go up and down. So the meanings of up and down will change if you change the location of poles and zeros. So in the next class we'll spend more time, but in the lab I would prefer that we go and physically design systems by placing poles and zeros, and always remember that wherever, if pole is at the center, then the length of the pole becomes 0. No, if it is, the question is, if it is pole in the center, length will not become 0. This is length. Okay, let's say here, this is the case. It is at 0.5 and this is the unit circle. So length of the pole vector is going to be 0.5 and length of the zero vector, so it will be V3 divided by V1. Now V3 is always equal to 1 because zero vector is always equal to 1. Now the pole divided by pole, so it is 0.5. So it is going to be 10 over 5 is equal to 2. So if you plot the response, it will be 2 at 0 degree where the pole is, and exactly opposite to this, it is 1.5. So 1 over 1.5. 1 over 1.5 is 10 over 15. So 5 2 is the 10, 2 by 3. So at 180 degrees, it will come down to 2 by 3. So this is how it is going to look like. Okay, so if the pole is in the center, then length of the pole vector, not pole, length of the pole vector will become 0.1 over 0.5, which is 2. So which is the max. So it will, this is how the shape will be. So it is length of the pole vector, length of the zero vector divided by length of the pole vector. I think I should stop here. And please in the lab just focus on these concepts, and I request Dr. Ali to give you a lab where you just first design a single 1-0 system, just put a 0 and play with it by changing its location. First just not changing R, only changing theta, and then just changing, not changing theta but just changing R. And then I would like you to do the same with a pole and see that how the frequency response is shaped and also the phase of the frequency response. Thank you very much. Inshallah, we'll see each other next time. If you have any question, please ask. I have already taken like few minutes more, but still if there is any question, I would love to answer that. Okay, ji. Thank you. Thank you very much. Khuda Hafiz.